Now we're going to have a look at something called binary search trees. Now how binary search trees work is that they are in itself a binary tree, but what happens is that they're slightly easier to search, and the reason is because they're sorted in a nice way. So let's take an example. Let's say we have a list of elements, so let's say it's 5 at the start and 1 at the very end, and we're trying to insert it into our binary search tree. So what happens is we insert the first element into our root. So that's 5 over here, and then we cross it out over here. Then we get a second element, which is 7, and we have to ask ourselves: is 7 greater than 5 or less than 5? Well, it's greater than 5. So we cross it out and we realize it needs to be in the right-hand side of the tree, because everything larger than 5 needs to be on the right-hand tree. Everything less than 5 needs to be on the left-hand tree. So 7 needs to get inserted right over here. Great. So then we come to the number 3. And so we remove it from our elements over here, and we ask ourselves, is 3 greater than 5 or less than 5? Well, it's less than 5, so we go left, and we have, oh great, there's a space here. We insert it in right over here. Now, again, we then say, okay, cool, that sounds good. Now let's look at 8. Now, 8 is larger than 5, so we go right, and it's also larger than 7, so we go right again. So 8 nicely gets inserted over here. Then we look at 6, and we say 6 is greater than 5, but less than 7. So it gets put in over here. And now finally 1. 1 is less than 5 and less than 3, so it gets put in over here. So this is kind of nice because if we do an in-order traversal, so if we do an in-order traversal of this particular thing, we do it in order, we're going to get 1, 3, 5, 6, 7, and 8. Now this is great because it's already sorted. So that's a great thing about a binary search tree. It's in order, it's already sorted. In addition, if you ever want to ask, oh, is, let's say, 2 in my binary search tree? Well, then I can just look at my 5 and then say, nope, and it has to be less than 5. So I then look at 3 and ask, is it less than 3? And the answer is yes, it's less than 3. Oh, but I only have one thing here and it's 1, and it's not 1. So 2 is not on my tree, and that took exactly the number of levels in our particular tree. This is great because it means that we can do binary search automatically in a way, which is exactly why it's called the binary search tree, or BST for short, binary search tree. Now, one problem is if we instead get a list of something like 1, 2, 3, 4, something already sorted, what you find is it looks like 1, then 2, then 3, and then 4. Oh no, this is not even a tree really, because we never had to go left. So that's the problem with binary search trees. You can sometimes have things that are what we call unbalanced. Unbalanced. And by that it means that there's one's half of the tree which is way bigger or has way more height than the other half of the tree. And so in order to counter this, we come to something called an AVL tree. An AVL tree is one that self-balances. Self-balances. So what that means is if it ever gets out of balance, if one half is ever larger than another half, then it readjusts everything and it moves the root, it changes the parent node and redoes it. Now, I won't go into how exactly it does that. You can watch videos and read about it if you're interested, but what you should know is that there are ways to keep it balanced. Like the one that we have up here, this one, is balanced because generally there's like the left-hand tree is the same length as a right-hand tree, and this left-hand tree is only just slightly larger than this right-hand tree, which is kind of non-existent over here. So that's why it's important to keep balance so that you can actually do nice searching, nice insertion, nice deletion, and an AVL tree helps us do that. Now, one more point I'm going to mention is that if we give each of these values an index, so if we give that an index of 0, an index of 1, an index of 2, an index of 3, an index of 4, an index of 5, and an index of 6. And then we can actually write this in a corresponding array, just like this. 0, 1, 2, 3, 4, 5, and 6. So if we put in these elements, we can say this is 5, this is 3, this is 7, this is 1, this is blank. So we can just keep that as none. And this is 6, and this is 8. Now this is actually an array way of storing a binary search tree, or in fact any binary tree can be stored in this way, where if you ever have a node, like let's take node 2, then the children of node 2 are node 5 and node 6. So the children of a parent, if this is I, are 2i plus 1 and 2i plus 2. And you can check that works anywhere. So in fact, you can always go from a parent to a child. And in the same way, if you have a child j, the way to get to the parent of it is to do j over 2, take the ceiling of that, and then subtract 1. And that's actually going to get you right back to your I. And so actually just using an array, a simple array, we can store our binary search trees, any binary tree, as a simple array. So this is very useful because you don't actually have to do any fancy list of lists, any fancy nodes and classes. You can just very easily store them in an array as long as you know how to get from a parent to a child and from a child to a parent. So that's all for today. Thanks.